Did it start? Okay, yes, it says recording. Okay, so I think the way I'm going to go through this, I guess it'll be pretty similar to last time. So I did go through before. I know that Rob posted his version of the equation sheet yesterday or Sunday night. Before he posted that over the weekend, I kind of went through from the mindset of one of you guys and went through the book and kind of wrote down equations and formatted an equation sheet the way that I would if I were taking this test. So I think I'll go through that first because the other equation sheet, I think you guys have seen a bunch. And then I can hit on some conceptual things and things that you might want to include for yourself on your own cheat sheet and what have you. I did have a student email me over the weekend. So I'll just also give kind of a blanket recommendation to you all that I think that it would be worth it just to kind of save space on your own sheet, since you just have one side front and back, to print out the sheet that he is providing and annotate and take notes on there. And then you can have one full sheet for specific things or bigger like graphs or pictures or diagrams or whatever to kind of connect the physical situation to the equation if you think that that's something that you're going to need. And yeah, that's one of my blanket recommendations. So let me share on my tablet because that's where I have my stuff located. Okay, so this is kind of, it's a lot. I'm going to zoom in and go through each section step by step. But if this was my page front and back, I tried to organize everything as much as I could into like blocks of the topics that you guys are going to have. Also kind of looking at the practice exam because he listed a whole bunch of sections from the book that there weren't necessarily questions on the practice exam that transferred over. There was also a ton of conceptual questions on the practice exam, more so than the past exams. So that's also something to keep in mind. So this is my first page with all the rotational and linear stuff. And then the middle column would be how you go back and forth and connect the rotational to the linear quantities if you can. Then we have conditions for static equilibrium, stress, strain, and fracture, periodic motion, and then the following page is just kind of like all waves. I also I mixed waves and sound a little bit because there's a lot of concepts that transfer over from one to the other and they're very connected. And just from an organizational standpoint, it didn't make a lot of sense to me to have like a whole section for waves and then try and fit sound. The first time I tried to write this out on paper, it was not very neat. But yeah, so those are kind of all the things that we'll go through. And of course, I should hopefully see things pop up on the chat if you guys have questions or like do the raise hand thing or just ask them. So let's zoom in on kind of this general overview. So I've kind of been toying with this for the past couple of weeks now as you guys have been getting into rotational motion of kind of having everything organized, since so many of the concepts for the physical quantities transfer from rotational to linear. It's just kind of a swapping out of variables most of the time. I figured it would be better to kind of have all of the blanket statements or topics kind of on the side, and then we have rotational, linear / translational, and then how you go between the two. On the rotational side, or just maybe generally, I'll mention, so everything that I have in light blue is kind of like my own little notes to myself for how to interpret these equations in case they're, on test time, maybe they're not super clear always. So like the first thing I have up here next to rotational is going to be the fact that counterclockwise is positive and clockwise is negative. So I'll always try and throw that on any type of rotational problem I have when I'm solving it, and just having it listed there is one less thing that you have to memorize as far as signs and directions for that those rotational quantities. I have the next two, so yeah, so these are just all rotational kinematics, linear kinematics. Hopefully those at least are familiar to you guys by now. The only thing different I have for these linear kinematics equations is I kind of generally put this d variable as a placeholder. So that could be like your x position, it could be your y position, it could be your arc length position. It's just a placeholder for position. So I mean, that's something that I put in like the little blue writing in case for some reason that was something I forget. And then going back and forth between the two, we get arc length from our angle times the radius, translational velocity from omega times radius. And then I also put on here, so we have translational acceleration as alpha times radius, but then you shouldn't see at this point centripetal acceleration being mixed with translational, but just in case, I know it's on, again, the equation sheets that he wrote. Everything from the previous exams is there in addition to the new stuff. So I also just threw centripetal acceleration in terms of tangential velocity, so our v squared over r that we know and love, and then also in terms of our angular velocity omega, so omega squared times r. Questions yet, or am I good to keep going? Okay, I'll take silence as good to keep going. For moment of inertia in mass, as far as like rotational and linear stuff, it's more so just the variables that change. Of course, as we go from getting moment of inertia, we have to get from mass and also where the mass is distributed. So I put the equation for if you have a collection of particles, or if you're in the case where you can treat your masses as a collection of particles. So basically not anything where you would have like a sphere rotating around its own axis or something like that, but kind of just like a whole bunch of points generally rotating around something, then you could go ahead and use that formula. Otherwise, you would just look up on his equation sheet for whatever shape you have, what the moment of inertia is. I probably should have included a little asterisk of like C chart for any other situation other than collection of particles. And then for moment of inertia, we also want to include the parallel axis theorem, which states that the moment of inertia at a parallel point to the center of mass is equal to the moment of inertia at the center of mass plus md squared, where that d is going to be the distance between the center of mass and parallel. All of those things also I'll mention could be things that you might want to write down. So like that the parallel, those two lines, that means parallel, that COM stands for center of mass, that CG can stand for center of gravity, kind of all of those things I feel like the professors can get a little comfortable with using, that maybe doesn't always transfer of like, what the heck does COM mean? So those are all things also that like I didn't make notes of, but you definitely could if that's something that you feel like you need. For torque and force, we have our Newton's laws equations for each of them. So our torque net is going to be equal to moment of inertia times alpha. Our F net in each direction would be mass times acceleration. And then getting to torque from force, we would take the cross product, which we can write a few different ways. So we have the magnitudes of force times the magnitude of radius times sine of the angle between them. I went ahead for this torque and for this work equation, I just called that angle phi, so it didn't get confused with that angle theta. Ooh, actually, now I kind of want to check and see what he has on your equation sheet. Let me go to Canvas real quick. Exam 3 equations. I did like that he highlighted some stuff for you guys. Oh wait, this isn't what I was looking at before. This looks new. Okay. Power, where is work? Okay, yeah. So like he has on his equation sheet, work by a force W equals FD cosine theta. I would maybe just and then also for torque, he has that angle in terms of theta. That's something that like I would annotate on his sheet to be like, for those two thetas specifically, it has to be the angle between F and R if you're going to use it, just so that you don't get that confused with like, say, an angle that you're traveling through, because we call that theta. So we're reusing a lot of variables for the same stuff. But we can also, if you want to just abandon that altogether, you can, of course, just do your vector breakdown and do either the perpendicular component of F times R or the perpendicular component of R times F. You know, I'm a big fan of those. Moving down to work. So work in terms of torque is just going to be our torque times the angle that we're traveling through. I didn't do the dot product specifically there. The only thing that's going to really change is whether or not it's positive or negative, because since torque can only be counterclockwise or clockwise, and theta can only be counterclockwise or clockwise, you'll either just have that overall be positive or overall be negative. Whereas for work in terms of forces, we have a lot more variation of how F and D can be oriented with respect to one another. So again, I have it written as FD cosine of phi, and then we have the parallel component of F times D and the F times the parallel component of D. For converting between the two cases here, essentially all that you would do is either get the force from the torque if you have the distance and then get work, or if you have the change in angle, you could get the torque from the force and then plug it in to get work. So all of those little asterisks that I have, like C torque, the one below that is C moment of inertia in kinematics, you're basically would just be plugging in conversions that I already have listed above to do that. So same for kinetic energy. We have rotational kinetic energy is 1/2 I omega squared. Translational kinetic energy is 1/2 mv squared. And if we wanted to put rotational terms in terms of in translational quantities, which is very, very common, you would substitute in, say, the specific equation for moment of inertia that you have. And then for omega, that would be V divided by R. But those things are listed above. So to save space, I didn't write them twice. And then last two things for kind of these general foundational mechanics equations are going to be our impulse and our momentum. So for our rotational, we have angular momentum is that capital L. So the change in angular momentum over the change in time is going to give us our average torque that's acting in that time period. And then we can also just write angular momentum as moment of inertia times angular velocity. We have all those same linear quantities. So the change in momentum over time is going to be equal to our average force that's being exerted over that time period. And then linear momentum is just mass times V. This is probably the only one. So everything above impulse and momentum, you guys have covered pretty extensively in the linear case. Momentum, I know, is new for this exam. So that's the only thing that I was like a little iffy about putting something so small. But you could put a lot of extra notes, either again on his equation sheet or on this one to kind of just fill in that section. Because the only other things that you really need to know are conservation on collisions, and that you would set initial equal to final if there's no external force. But for me, I could get away with just having those two equations, and I know that I would be okay. But if you're a little less comfortable with knowing exactly how to apply those equations, I would definitely put a little bit more for that momentum stuff. And then as far as going between linear and angular momentum, if you can treat the object as if it's a particle, just some distance from the center that it's rotating around, you could just write angular momentum as MVR. Otherwise, you have to use the specific moment of inertia and do that. So same as for kinetic energy, you would use the moment of inertia equation for whatever object you have to sub in for I, and then for omega, you could put in V over R. If, say, for some reason they were asking you for a linear quantity, but they gave you angular momentum, that's how you would do something like that. But yes, so that was very fast, but I know that we've kind of beat these with a dead horse for the past couple of weeks. So any questions on any of these rotational or linear quantities or going back and forth between them? Fantastic. Okay. So then I'll zoom in to fit the screen for these ones because I had to start to squeeze so that my chart looked neat and organized because my OCD was kicking in hardcore. But so underneath that, I have the conditions for static equilibrium. So just that the sum of the forces and the sum of the torques all have to be equal to 0. Just a nice little tidbit I think to have there is the fact that the torque can be calculated using any point as the origin. So that's just really helpful when solving those types of problems. If you have multiple unknown forces, it might be advantageous to put your origin at the location of those unknown forces, because then when you're calculating torques, the radius would be 0 and you don't have to worry about them. Other things that you might want to mention on here if you feel that you're having a hard time remembering them, also just because the test is, or the practice at least, was very conceptual, are going to be the definitions for stability. So the unstable, stable, and neutral equilibrium positions. If you want to just like put a blurb of what all of those mean, that might be worth doing. And then kind of similar for stress, strain, and fracture. So I put the equations for stress and for strain. They don't have variables, so I just use the whole words. And then if you have stress and strain, we can relate that to Young's modulus, which we call capital E here. And then I just rearrange those equations to also set that equal to the variables that we do have, or the quantities that we do have variables for. And then I didn't see a ton of this on the practice exam, but I know just from doing the homework and working with you guys, stress, strain, and fracture is not a topic I'm as comfortable with, even as an instructor, because it's not something I learned super well as a student. So maybe having the 3 different types of stress, so compressive, tensile, and shear, and potentially just what those different things mean. So compressive is when you're pressing down on something, tensile is when you're pulling, and then shear is when you're kind of going at an angle. There could be a conceptual question on that. I also had something in my own notes about the like maximum compressive strength and the quality factor and all those sorts of things. That kind of falls into the category for me where I know you guys did it on homework and it is a good concept and you should know the concept, but I highly doubt that that's going to be a question. And if it is, it's only going to be one. So risk versus reward, not the most important thing I feel like that needs to be on your equation sheet. But if you have the space and you feel like you do need it and it is important to you, then put it on yours. Okay, and then this was super squished, but I think it worked out okay. So this is all the periodic motion or simple harmonic motion at the bottom. I kind of put, so I have the equations for position, velocity, and acceleration. I know he had to put them on your equation sheet in terms of the period. I just put them in terms of omega because it's a little bit easier to write and saves a little bit of space. and I also didn't include the phase angle because he didn't include them either. So that also includes some, or saves some space for us. And then I think it's just nice to have on the side what the maximum position, maximum velocity, and maximum acceleration would be in terms of that amplitude and the omega. So I have those listed to the side as well. And then to the left, kind of super small, I just have some of those definitions for those characteristics of the wave. So what are just the fact that capital A is amplitude, little f is frequency, and that means cycles per second. And then that capital T is period, which would be the time per cycle. And then I also included just a very tiny sketch of what one period would look like for the position. So you could kind of also see that it's oscillating between the positive amplitude and the negative amplitude. It's coming back to the same state that you were, that constitutes a period. And then from the discussion section, I know that we saw some problems with, going from the starting point to that first zero. If you have a graph like this, and you could fill it in even a little bit more, you could put like where the period, a quarter of the period corresponds to that first crossing of the zero axis. At that minimum negative A, you would be at half a period. And then when you cross the zero again, that would be 3/4 of a period. Again, customize as you feel that you need. And then underneath all of that, I just have some of the relationships between omega, frequency, and period. Those would apply to any periodic system, but then we do also have omega equations for omega, whether you have a spring mass system or a pendulum. I know that on his equation sheet, he's including, let's see, he includes just for a spring mass system, it looks like, the period in terms of that square root and the frequency in terms of that square root as well. Oh no, he has them both on here. I lied. Since the omega angular velocity is related to both of those, and I have that equation at the bottom in order to save space. And also I think personally, so the period one just has a 2 pi, let's say for spring mass, square root m divided by k. Frequency has a 1/2 pi. For me, with all those fractions, that's just a calculator error waiting to happen. So I would say the better route to go would be to calculate omega first. And then if you need frequency or period from that, we have the equations in that middle section to do that. And then the last thing that I have on here for periodic motion is just the energies. So since the total energy is constant as this thing is oscillating, we can write our total as either the kinetic energy plus the potential energy at any point in time. And then we have our special points of it all being potential energy when we're at the amplitude. So we can also write E total as 1/2 Ka squared, or when it's at the equilibrium point and we have all kinetic energy, then we can write our E total as 1/2 mv max squared. I guess this would also be something that you might want to put that I didn't on here. Since it's in terms of this kx squared and then ka squared, that is just going to be for a mass spring system. Yeah, which is always, I'm sure you guys have noticed, is much more heavily hit on than pendulums for simple harmonic motion anyway. Okay, I'm going to take a sip of coffee before moving on to the waves. And any questions on this page overall or periodic motion?
The E total, the first one, like the first equation, what situation would you use that?
That would be if, say, oh shoot, if for some reason they like gave you actually I know this was a homework question, but I don't remember what number it was. It was like they gave you the x at like some time, I don't know, I'll just draw a dot on here. If they gave you like the position and velocity at any other time, except for the points of interest. So whether you're at, so the amplitude or the equilibrium point, then you would use the velocity and the position. I won't be posting my equation sheet to Canvas, at least not before the test, just because it's a good exercise for you to go through and write this stuff yourself. But definitely go ahead and take notes. And I mean, this video is going to be posted, but I feel like I would be doing a disservice if I didn't make you guys at least copy down this information for yourself to help you retain it a little bit better. But okay, did that answer your question about energies?
Yeah, thank you.
Okay, you're welcome.
All right, so on the practice exam, there was a question about a uniform hoop of radius r and mass m. So are we expected to know the proper?
No, yeah, you wouldn't be expected to know those. And I know he didn't put them. Let me double check. Yeah, so like the new exam 3 equations, which I feel like I could have sworn looked different yesterday when I looked at them, but they don't have all of the, like that chart of the different shapes and their moment of inertias, but that wouldn't be something you guys would be expected to memorize.
Okay, so it'll be given.
Yeah.
Okay, thank you.
Okay, I'm gonna move on to our waves. Okay, so for the first part, and maybe I'll just go over the graph first. I did think just because there's so much new vocabulary and definitions when going into waves, a lot of the periodic motion stuff transfers over to regular old waves and sound in the time domain. But now we also have the space domain to think about since wave travel in space and time. So I also just drew another little wave so that way I could go ahead and label what nodes are, what antinodes are, what peaks and troughs are, the wavelength, all of that kind of good stuff. So it's all just nicely summarized for myself to look at. We have the wave speed or wave relation equation at the very top that applies to all waves. So that's why I also kind of just generally threw that at the top. And then for waves on a string, we have that the wave speed depends on the tension and of the mass and length of a string. So again, like kind of in the blue, just in case you absolutely need it, if you have mu as m/L, you might just want to make a note that that's specifically the mass of the string and the length of the string, just in case they give you some like random ass mass that has absolutely nothing to do with calculating the velocity. Just so you're not kind of just blindly plugging in, hey, I have a mass, so let's put that in for my calculation of wave speed. And again, so now this is where things are going to start to mix, because I also felt like this was a better place to put the speed of sound and air, since it's calculating the wave speed based on the medium that we're going into. So for speed of sound and air, that's 331 plus 0.6 times the temperature. So that capital T is not the same as the period. That's going to be our temperature, and that has to be in Celsius. And before someone asks me, you would not be expected to memorize the conversion between Celsius and Fahrenheit. I also would hope that they wouldn't be so mean that they would give you something like that on the test. But when I review the test, whenever it comes out, if that's on there, I'll make sure to speak up for you guys, because that would be just rude. For intensities then, the only thing that he talked about, or what I saw in the book when I was looking through, and I'll double check on his equation sheet here. So this is a concept I would say that you definitely should know, but he didn't put it on your equation sheet, and that's that the intensity is proportional to the amplitude. I feel like that's always something that they typically talk a lot about, but they don't always necessarily ask a lot of questions about, because they don't give you the full equation, they just give you that proportionality. And then the other thing that he gave you on the equation sheet that's different is the intensity as a function of distance from whatever source is producing the sound. So the full equation for that I wrote down here is power divided by 4 pi r squared. He gave it as I is proportional to 1 over r squared. So maybe something I'll put on here then that's actually useful, that's a little bit better than that would be, so if I is proportional to 1 over r squared, if you have a ratio of intensities, that would be I1 over I2 is R2 squared over R1 squared. So I would highly, highly recommend that you put that somewhere. And then also with intensities, we have calculating the sound level from intensities. So I do have that beta equals 10 log I over I0, where I0 is just 10 to the minus 12 watts per meter squared. The other thing I included down there, just again, if you guys need it, is how you would get rid of that log if you were given a because I know on the practice test, they gave you a question where they gave you the intensity and you calculated beta. But I think you're more likely to see the other way around where they give you beta and you have to calculate I, and then it's like, how do I get rid of this log? So you would do that by exponentiating both sides. So if you take 10 to the power of log of something, that just pops out whatever's inside the log by itself. So that's something that I put on here for myself to kind of just, in case that situation comes up, how you would get rid of the log if you needed to. And then the last thing really, or I guess there's more than this, but harmonics are huge. So I did a whole big section on harmonics for myself. So for any type of harmonic, whether it's a string, whether it's a pipe or anything else, that Fn equals n times F1 is always going to hold true. So that's basically your resonant frequencies are equal to whatever your wave number is times the fundamental. Oh, maybe that's something else I should put on here. So this F1 would be the fundamental. So that's another thing that might be useful to have on there. But then as far as the wavelength, that's going to change depending on what system we have the harmonics or the standing waves on. And then, so the way that I broke these down is we have string, open pipe, closed pipe. I have a little sketch for each of them with the fundamental. And then in the light blue, it says the rules for basically how you have to draw these. So for a string, you need to have nodes at either end. So you can have much more nodes, obviously, if you go into higher harmonics, but you need to have at least one at each end. For an open pipe, you need to have antinodes at each end or at the openings. And then for the closed pipe, you need to have an antinode at the opening and you need to have a node at the closed. And all of those have the same length. Then if you're able to draw the picture and you feel more comfortable drawing the picture, you can do like in discussion, you know, if you draw the wave and you could count the number of wavelengths, that number of wavelengths, then you could just set equal to L and you could find wavelength or length depending on what they give you and what they're asking for from the picture itself. But what you're supposed to get from these pictures is that you can get these relationships for the resonant wavelengths in terms of the length and that wave number n. And then just the rules for that based on the geometry are going to be slightly different for strings and open pipes than it is for closed pipes. So I just have those all listed out. The only thing I really feel the need to make note that isn't just written on the page is the fact that closed pipes, those ends have to be odd. So I listed them the same way that they typically are listed, where for string and open pipe, n could be 1, 2, 3, up to infinity. but for closed pipe, that n can only be 1, 3, 5, 7. It can only be an odd number. So if you need any sort of like extra notes for yourself just surrounding that, I would definitely make sure you do that. Because I'll also say, so even if you have a closed pipe and they ask for the second harmonic, that's still going to be, it's not going to be n equals 2, it's n equals 3 for the closed pipe, because the next harmonic after the fundamental is going to be 3 and not 2, but it's still called the second and not the third. So just be cautious when you have closed pipes. And then let's see if he changed this now. So I also did beats after Doppler. So my bad. I know that's not the order he put it on here, but whatever. So there's a lot of different ways that you can write the Doppler effect equation. I'm not a huge fan of most of them. So this is probably my favorite way, just because if you have the source and the observer both moving, you can account for them in the same equation. And then also that plus and minus in between, or in the numerator and in the denominator, won't change. You would just change the sign of your value for the velocity of the source and the velocity of the observer based on whether or not it's approaching the sound or if it's retreating from the sound. So, and I put little notes for the signs, at least one half of the sign convention on the side, so that V source is positive if it's approaching the observer, and V observer is positive if it's approaching the source, and then the opposite would be true as well. So it would be negative if V source would be negative if it's retreating from the observer, and V observer would be negative if it's retreating from the source. Based on the versions that he gave you on the equation sheet, I would probably guess that you're not going to have situations where you're going to have both moving. So he split them into the cases of observer stationary, source moving, or observer moving, source stationary. He did also include that sign convention a little bit for approach and recede, which I hadn't noticed, which is awesome. And then he also included and wrote it the same way as I did, where that V, S, N, D is the speed of sound. So cool. And then the only other thing really that you guys have is then just beat frequency. And the important thing to note with beat frequency is that it's the absolute value of F1 minus F2. So if you're given the beat frequency and then F1, let's say, and then you're asked to find F2, just keep in mind that there's going to be two possible answers. So if the beat frequency is, say, 3 and F1 is 40, F2 could either be 43 or 37. Since you're taking that absolute value, either way, you'll get back the same thing. So just be a little cautious with beat frequencies as well if you're solving for one of the frequencies that isn't the difference between them. Maybe that's something I would also put on here, is that sometimes they call it the difference frequency instead of the beat frequency. So I'll also throw difference in parentheses. But yeah, that's pretty much all that I had. So maybe I'll zoom out of this to do an overview of what this sheet looks like. And any questions on second page, first page?
I was wondering if maybe we could do an example of a time when beat frequency would be like which answer would be the correct one and the absolute value.
Yeah, so I'm not going to go through I'm not going to do a full example here, but basically what you would need to know is they would have to give you another piece of information of whether or not the one you're solving for is higher or lower. That would be basically it. So if I said
Okay.
that, yeah, that the beat frequency is 3, find the larger frequency that could make this true. If F1 is 40, then that would tell you, oh, I need to use the 43 instead of the 37.
That makes sense. Thank you.
You're welcome. But I know, I forget, we went through that on Friday. It was like some really pain in the ass ranking problem in your homework. That it was like the answer was, I think they gave you the beat frequencies in the F1 and they wanted you to rank then the frequencies of the other members of this guitar thing. And the answer was that you couldn't. So that's also kind of the reason why I bring that up, because if you have a conceptual question, I feel like that would be an easy conceptual question for them to do, where the answer would be like, you can't calculate F2 technically because you don't have that extra piece of information of whether it's above or below.
That one was really hard. That's a good thing to note. Thank you.
It got me. I
Me
was
too.
embarrassed. Caitlin was there. She saw it.
Yeah, for that problem, I was going like, you know, well, this one, the difference is 0. So, I mean, absolutely, it would have to be, yeah.
Yeah, I totally forgot that that was even an option to click for those ranking problems. Oh, yes, and I don't know. You want me to zoom in on the chart itself, Caitlin?
Yeah, that would be helpful.
Okay. Let's see. This is also, so I know this is in my handwriting, but I have a very similar, if not identical chart in the rotational work energy and momentum video that I just posted. It's like, you could take a screenshot of it at the end also. So tip for, and yeah, it doesn't come up as clearly on here. I could see it on my screen versus on my tablet, and it's just like a little blurry. Oh yeah, and the freaking, okay, and momentum. Oh no, it's there.
Okay.
Could we work, sorry.
Go ahead.
Could we work through a problem on the practice exam?
No, I'm not gonna do that
Okay.
now. But if you give me a heads up so that I know what I'm in for on Thursday.
Well, it's just problem 6, so it would be simple. So nothing to prepare for, right? So
So just to make sure like I'm understanding like your equation relations. So on the left, it's what it is in rotational terms.
Yep.
And then the far right is like linear and translational. And then the middle is like the relationship between the two.
Yes, exactly.
Awesome.
So I'm not entirely sure. The professor said that we get 2 pages, and I think he said front to back. So could we have the printed equation sheet on one side and then just have our own stuff on the other side?
Yeah, I'm a little actually confused about what exactly he is meaning by some of this. I think that that's what he means, that you can have one sheet that's his front and back if you print it double-sided, and then you can have your own front and back. That's the gist that I got.
Okay.
Yeah, and let's see what else he has on here. So yeah, so I mean, a lot of what I have is the same as what he has. The only thing, Like there's just some format things that I'm not always a huge fan of. Like for the standing wave, he lists all the fractions out on a single line, which doesn't always make it super clear what goes in the numerator and what goes in the denominator. So like that's the type of shit that I would just like rewrite it either directly on the equation sheet or just make a note of like the velocity is in the numerator, even though it's outside of the parentheses. And yeah, and he has some of that stuff just because I didn't go super in depth with the momentum, like the momentum conservation stuff, notes about elastic versus inelastic. Those are things that I forgot to put on here as well. I didn't put power on here. Shit, man, I missed a lot. Okay. Sorry. Sorry, guys. But yeah, those are all things that you could probably add on here as well. But otherwise, if nobody has any further questions or wants me to move around to copy anything else down that I have on here, I'll probably go ahead and wrap this up and upload it for the rest of the class.
I'm sorry, really quick, just clarification on one of your symbols here for the moment of inertia under rotational motion. The two lines that's just resembling the parallel axis.
Yes.
Is that what that's?
Yeah.
Okay. 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 Great. Thank you. Thanks so much for doing this. It's definitely been really helpful. Really nice of you.
Oh, you're welcome. I'm happy to help you guys out. I know it can be very stressful.
Yes.
Alrighty. Well then, I guess that's it for today. I will see you all on Thursday, and I will post another announcement on Canvas with all the new resources as they're ready. So hopefully that'll be up by later tonight.